Okay.
We will take only one midterm.
You're not in the E&M class?
Yeah.
Oh, so, oh, you didn't know that.
Only one midterm.
That kind of this one. You didn't read the syllabus, huh?
No,
That's how you'll be questioned.
I think there's no online. I mean, there's no website. Okay,
Oh, yeah.
give a page, so I can most probably attend.
Got it. But there must have been a syllabus, right? But then in the
Yeah,
beginning,
yeah.
there are so many syllabuses that come
He
across.
gave us.
I don't even think it mentioned it other than just the percentage on it.
Oh, I see.
But
Yeah, okay.
we found out the date for our midterm like a week ago.
Ah, yeah, but that's common in graduate
Yeah.
courses. Yeah. It's just, I mean, I try to keep it fixed because it's just less hassle. Like it's kind of a clarity, right? If students have clarity, there is less number of emails that's communicated. So for me, it is like, no, don't ask me too many questions I don't have answers to. So, okay. Yeah, so the discussion is about having another midterm, and that came up because you guys have an E&M. So here's my proposition. I was going, okay, what I want to cover this semester is I'm doing complex analysis. And usually what I typically do is right after this, I get into differential equations, primarily Green's function. And that takes about, I mean, it can take forever, but I mean, 4 weeks is good. At least one decently can do this. And if I do complex analysis also, it takes about 4 weeks. There are sufficient things you can go around. And we are only halfway in complex analysis. That could be 2 weeks easily we can spend time on. And this semester, I was hoping that I can do Dirac delta notation in quantum mechanics as part of a math methods course, just probably 1 or 2 weeks. It should be easy enough, and it will be very useful for you in other places. I try to do this because once, or at least I've heard that the notation turns out to be a significant hindrance in learning the subject. Of course, the subject itself is hard, no doubt about that. Yes.
Why not linear algebra? I mean, it is relation in quantum mechanics. And
yes. So, okay. Probably that's what I will do exactly, but I don't want to give a word of linear algebra because that's a vast subject. Like again, I'll have limited time here. So you can say I will do linear vector spaces in the context of physics, mostly in the context of physics. So almost I don't want to start with the axioms and all that. I'll immediately come to vector space and talk about what Dirac delta notation is and how it is used in specific examples where probably it, a good bit of the whole of our education processes that repetition is necessary. First time you see, oh, this is, I don't understand it. Second time, oh, you get used to it. This is what it was. And third time, oh, okay, I get a feel for it. And it's a never-ending process all during research year. Oh, this is what was meant when I was supposed to be understanding this in undergraduate. So it's a never-ending process. So hopefully this will one step towards that in that sense, I would say. So the context or the point here I'm trying to make is that today in the morning I was looking at what to do today. And then I was thinking, okay, I need to cut on something on complex analysis so that I have more room later on in the semester. And I was thinking of dropping something in complex analysis. So I can, since we have videos last semester, and since I have homework sort of ready from last semester, I can make it a midterm exam, take home midterm exam, where you watch the video and you do the homework, correct? And that will act as a midterm exam. So it will pretty much be a, if you want, take home midterm exam or a take home homework, or it's like a homework, but in the weightage that we have in this course, it will act like midterm. So it dilutes your midterm grades if you're not satisfied with your midterm grades. That's usually one of the motivations from what I gather from students' perspective. I'm sure they don't want midterm exams. It is usually to bring down the average, that you increase the number of midterms. And I'm sure there is a learning component to that also. So if answer this question to me, that you would prefer a midterm. So there are two pieces to the midterm exam. One is the grades, right? And grades come to neutralizing the earlier midterms, averaging out. And the second part is you get to learn during, so you're compiling all the knowledge you have on the, let's say 2-3 days before that. And that also is a good component of the learning process. Is the first and the second important in you guys? Like, is that important, that second place where you can collect all your knowledge? Then what I can add is that I can add a small, let's say 20% of your grades will be on an actual test. 80% is on the homework, and 20% is so that you guys sit and collect your knowledge and I take a test. Is that, would you like to have that? If you guys don't want that, I don't do that.
I want.
You would like to do that?
Yes.
Ken?
Honestly, I'm just kind of confused on the
Okay,
question, but I definitely prefer having to sit down
and collect your,
collect the knowledge and put it all on a paper and not look at my notes and make sure that I understand the material.
perfect. So that, okay, so that answers my question. That was my question as to, in a midterm exam, there are two parts of it. One is taking the exam, actual exam, and scoring and getting an A and or a B. And the second is what I was trying to say, that you collect your thoughts. That's an opportunity you have to get all your homeworks together, all the knowledge together. And just those collection of thoughts also is part of knowledge. I mean, believe it or not, it contributes to some learning somewhere. It's like writing a paper over doing the research. After you do the research, when you write the paper, that's a significant part of when you're communicating. You say, oh, I missed this. So it kind of fine tunes the whole thing. So I feel that is important, but I don't, when I'm teaching, I don't care about it so much. But more recently, I've been thinking about that. And so from what I hear, all of you guys, I think all three of you and Rob, we'll put a vote from him also. So 3 out of 4 anyway. And so, yeah, so let's have a midterm. The midterm 2 will stay as it is, the same date, but somewhere along I will have a take-home part which will deal with a content that we won't see in the course this semester, but it will be a take-home in that sense. And we will have 20 to 25% of the midterm decided by an exam, which makes you collect all your thoughts together. What if I ask you to, suppose there is an exam and I ask you to compile your knowledge on what you have learned, right? You write a write-up and submit to me, or you guys prepare and I ask you a question. You see what I'm saying? The preparation for the midterm, if preparation is more important, why don't I ask you guys to make a write-up? Doesn't have to be formal, doesn't have to be typed up, but whatever you do for your preparation, you show me that you really prepared and you really worked on it. Will that lead to you guys less preparing less? Was that clear? Yeah. So the question is, we agreed on the fact that you guys preparing for the midterm helps you guys a lot, correct? That's what we concluded. If that is the case, is the real test taking important? Like, if preparation was more important, then is the real test important or the preparation was more important? So I can understand that if the test component is taken off, you will not work. right? The whole motivation for that is gone. I do understand that, but probably it's harder to answer.
It's a hard question. To answer.
Okay. So
Because,
let's, yeah.
in both instances, you are really preparing. It just really, I think, depends more on the individual as far as the write-up goes, right? So like, how far are you willing to go into understanding it?
Correct. Because many things you will just read and register it, and sometimes you're spending unnecessary time listing things. Okay, let's stick to the exam. We will have a 25% exam, midterm 3, we will call that. 25% of, that's a complex analysis, so something like that. And I'll come up with a date and how to do it and how should we distribute it somewhere so that it doesn't really come on the previous day of midterm 2. So we will do something about that. It will be somewhere in November. When is midterm 2, by the way?
November 4th.
November 4th, right? So this will be, yeah, November 4th, maybe. I mean, the only time is November 19th or something, right before the Thanksgiving.
Right.
You guys know that there is a Thanksgiving break. You guys, this is the first semester for you. There's a Thanksgiving break. It's almost 10 days. It's 9 days actually.
Really?
Like you start from, like, it's a whole week plus Saturday, Sunday. Yeah. So it's between 2 weekends and the days between them. So it's 9 days, and it is right before the final exam. Right means the second week if you count backwards from the final exam. So be aware of that. It's if you want to do something, that's the time to do, even preparing or yeah. So that's a good.
So we have 2 weeks after we come back from exam.
After you come back, you have 1 week of classes,
And then
and the second week is exams.
Oh, wow.
Yeah.
Okay.
So it's almost yeah. More recently, that's what is happening. What happens is that every year the day of classes go backwards. And then I don't know when they reset it. Once in 10 years, it's reset back by 7 days. So currently it is on the extreme end where the exams start on December 7th or something. Eventually it shifts. Like then it will again start on December 15th, so that Christmas holidays are reasonably not very too far away. And then it keeps shifting.
Right.
I don't know when that's reset, what happens, so, because somewhere you lose a week. So I don't know what happens there. I haven't been here that long. Okay, so let's do some examples, some contour examples. The homework, now that we decided on midterm 2, there might be some room for me also. I should ask Rob how it is on the. I write with small chalks these days. Okay. So you have homework 6 due Tuesday. How are the homeworks spread out? Is it sufficiently spread out, or is it too far away? Is it too less homework? Too much homework? Since you guys are talking about these things.
I like the homework. I think having a homework every week is really nice personally.
And it is sufficient, it's not too much, it's too less.
Sometimes it's
Either way.
And then, your willingness to push it back if I think
okay.
I think it's a perfect system.
Okay. So we can go with as we are, I think. Okay. Yeah, we did Cauchy's theorem. Let me see what the Cauchy's theorem is. We first defined what is an analytic function. And analytic function, there is an algebraic way of checking whether it's an analytic function or not, and that is what is called Cauchy-Riemann conditions. But always remember that Cauchy-Riemann conditions are not sufficient conditions. It's a necessary condition, but even after you satisfy Cauchy-Riemann conditions, you could have situations where it's not analytic. So that's important to remember. But surely if Cauchy-Riemann conditions are not satisfied, then they're not analytic, for sure. Right? That's it. But once you have analyticity, and analyticity, remember, of course, if it's a fully analytic function everywhere, then it's good. But most of the time, what you have is that in some region it's analytic, somewhere else it is not analytic. That raises the question as to give an example of a function that is that is analytic everywhere on the complex plane. Okay, everywhere, even as you get close. I mean, remember that if a function is infinite at any point, it's not analytic. Then basically the idea is from all directions it has to come in, and it's not easily well defined. So if a function is infinite at some point, then you immediately say it is not analytic at that particular point. So I was asking the question, what are the functions that are analytic everywhere on the complex plane? Okay. And can you think of any function? Answer is not easy, it is not logical. It is more of a popular level thing. So, but I'll ask the question anyway, just so that you guys get to think it a minute.
Exponential.
So this is exponential of z. That's the closest you can get. That's very good, because you would say that that's stuff. But notice that as z goes to infinity, at somewhere in regions, you will have this going to infinity. For example, x equal to positive x, positive real line, right? And y is equal to 0. So on the real axis, as you get farther and farther, x grows, then exponential grows, so it's infinite. So at the very far end also it matters. Is that clear? So it's a very good example. That's the closest you can get to that. So you're saying, let's say this is really the infinite. This is the real boundary of the complex plane. So on that, at this point, this goes to infinity. Okay. So we want functions. So when I say it is analytic everywhere, so this is analytic almost everywhere except at the boundary. At the boundary of that. So it grows in that. So in that sense, you're actually including that complex surface of it's not a surface, curve representing the complex plane also into picture. And the answer is no, there is no such complex function which is analytic everywhere, including this boundary. And this is the best example you can get. So it's a good answer to that, except a constant function, right? And a constant function is just flat, just 3 f of function is 3 constant function everywhere, then it's okay. Okay, so what's an analytic function? If you're told that there is an analytic function everywhere, which is analytic everywhere on the complex function, it's just a constant function. And this feature that it is analytic also has this, I won't cover on it, as this interesting geometric picture that because Cauchy-Riemann conditions constrains the function significantly, when you say that a complex, this is a curve, right? It seems like there are lots of points, but actually there are not a lot of points. If a function behaves in a certain way on the boundary, that defines the whole line in itself. So that's not straightforward to see because this is a curve, right? I mean, but the whole curve behaves as a single, it has a property that is very single. It acts like one point. That's the best I can say. And that's primarily because of the Cauchy-Riemann conditions coming in the sense that, let's say this better. Because of the Stokes theorem that we have, right? On a boundary, everything should add up to 0. The whole boundary will add up to 0. When we do the analyticity of a function, we might see this again at that time. I'll try to clarify this better. But currently, just see it as a broad jargon I'm saying is that the whole boundary behaves like a single point. Yeah, with that, let me proceed. Let me not get stuck here. Okay, so if it is an analytic function in a region, then Cauchy's theorem is that. So suppose you have a, and let's say that is a region. So this is marked by a contour which is going in the counterclockwise sense. And if the function is analytic everywhere in that, then we have z f of z equal to 0. If f of z analytic inside of the, and remember the sense of the contour, it is counterclockwise. That's important. When it is 0, it is not really important because whether it's counterclockwise or clockwise doesn't matter when it is equal to 0. But later on we will see when it's not 0, it will matter. Okay. So that should be easy to see. Now let's say, what if it is not analytic? And let's take some very simple situations, what happens. And we started on this last time. So let's consider the scenario. What is this equal to? Let's say A is equal to C Z. Now we say f of C over Z minus A. Now here, and let me specify that let f of Z analytic inside onto C, and Z 1 over Z minus A or 1 over Z is again analytic everywhere except Z equal to A, right? So 1 over Z minus A is analytic everywhere except Z equal to A. And these kind of non-analyticity, where it is only at one point, and that too because it is blowing up to infinity, is called a pole. And we will see why it is called a pole, because this is a special case which can get cancelled like that. I mean, remember when we go to, when something is blowing up to infinity, it can blow up to infinity as 1 over x, 1 over x square. When x goes to 0, 1 over x goes to infinity, 1 over x square also goes to infinity, 1 over x cube also goes to infinity, and they are all different kinds of infinity. And this is one kind of that pole, and we will see that this can get cancelled with something and it can give you a finite thing. So that non-analyticity can be captured in a sense. So that's what we want work here. So we want to evaluate this integral on the contour C. There are two possibilities, that this contour C has Z equal to A inside it, or it does not have inside it. If it is not inside it, then it is no, it is, this whole thing is analytic everywhere, right? So if Z equal to A is outside contour C, then what is I of A equal to?
0.
It's 0, because if it is outside, then it is analytic everywhere in Z. So then you go back to Cauchy's theorem and it is 0. That's a straightforward thing. So now we want to do, what if C of A is inside? All right. And I forgot to finish this. So if it is inside, then we change our contour a little, or we interpret the contour slightly differently. So so that's your contour C, that's Z equal to A, let's say. That's Z equal to A, and that's your original contour. And we interpret this contour as, I can somewhere from the contour, I take I change my route and come and take a circular path around point A. So I come in, go in a circle, again in a counterclockwise sense, and then go back. So when I come in and go back, they cancel each other, that path. Like whenever I come in along one path and then go back along the same thing, this contour is plus or minus, right? When I'm changing the direction. So this doesn't contribute. So this whole thing is the contour C itself, and there is a contour C prime, let's say. This is your A. A is that point. Is that clear? Okay. So I can say, one can conclude that what is the value of the function when I go dz plus z prime, and this is f of z over z minus a. Notice that when you're talking about C, you're having the whole region. So maybe I should clarify this. Then I'm having the integral on C that represents, this is your C, right? That's your C. And when I'm talking about C prime, I have a circular region inside in here, and this original C is here, and this is my C prime. And that's a region that encloses this. When I do C plus C prime, or should I be doing C minus C prime? Is that important? Help. So there is, remember, C can be transferred into the boundary. There is a contribution from here, and there is a contribution from here. So the point is C plus C prime. I want to argue that, why am I getting, so this is the same as if I want to argue that, is it necessary that it should be C minus C prime?
If it's inside the C curve, then
Yeah, because C has this region inside, right?
Yeah.
C prime is this. Okay. So, that's where, okay. So remember that this is surface S plus S prime, right? Where S is the surface and S prime is the total. Sorry, S prime is the surface. So this region is S, and this is S prime. S includes S prime in it. All these contours came out of a surface. Remember? So it is S plus S prime is the same as, or let's say S minus S prime, right? S minus S prime is the same as this region. So this is S minus S prime. Minus of S prime. Is that clear for now? Okay. But I want to convert this into C plus C prime, the contour. This gets related to C in the clockwise direction. This gets related to C in the counterclockwise direction. So let's be clear about this. So in this way of saying, I should keep this in the counterclockwise. So let me keep that in the counterclockwise direction. So it should not hurt me in my analysis, but apparently that's important. So let's have this, and I want to go in the clockwise direction. So this is C prime. So we'll see where it comes. At this stage, it seems like it's important. Right, so this is C prime, so I am going in the opposite sense. Right, so that's C prime, and I do C minus. What do you say, C plus? Yeah, it is C plus C prime in the sense now I changed the direction of the contour, so it is still C plus C prime. Okay. So that's your C, and this is my C prime. But what is the integral C plus C prime equal to? What is this equal to? It's equal to 0 because of Cauchy's theorem, right? Because it's analytic everywhere else. We said f of z is analytic everywhere. Z equal to A is analytic everywhere except that point, but I excluded that point. So this is equal to 0. So that means I can, now we have a relation. Oops. Okay. So put this in there. So this means that integral of C dz f of z minus a. This is what we want to evaluate. We would like to have a value for this. Plus or minus, capital here. We said plus, right? This is plus, but now this is going in the counterclockwise sense. Right. This is equal to plus C prime going counterclockwise. Z f of z minus a is equal to 0. Okay. So let's give it a name here. We had a name here, so that is function I of a. So that's your function I of yes.
So C prime is clockwise.
Yeah. So C prime is clockwise. Yeah, I meant this like that. Yeah, I think in my head I had it. Yes. So this is clockwise, but I want to switch to counterclockwise in the next step because that's how this is so that I can put the sign inside in there. Yeah, thank you. Clear? Any confusions? Okay. So if this is 0, in the outer region it is 0. So this function becomes equal to the small contour, right? Because of the Cauchy's inequality. So I of a, this is nothing but I of a. I of a, which is what we were interested in. This is equal to minus of that, the minus of C prime going clockwise. Z Z minus a. And now I want to make it clockwise. It's confusing. So this is C prime clockwise. And then I will stop writing it, counterclockwise. But that's our standard notation. So I don't have to specify it. Like any contour in general is counterclockwise. I had to say this is clockwise because this is not the normal convention. So this is the opposite convention. So I had to say that, but now I'll stop. And that I will start saying is C prime f of z. This is to clarify that I'm dropping the notation, that I'm going to not write counterclockwise anymore. Okay, clear? No confusions? Sorry about that.
So
yeah,
I of a is equal to or
is equal to. Did I define that? Yeah, I noticed I defined here. Right, so that's my IFA. So this is what we want to evaluate, right? We would like to evaluate. Oh, actually, that is equal to 0. Sorry. Oh, what did I say? Oh, hold on. No, this was not I of A. That was on the contour C is I of A. This is C plus C prime. But that's not I of A. That's C plus C prime. So that's a confusion. But here, this is I of A. Right. So there was a C plus C prime, which is analytic. This is, we don't know what this is equal to. This is not necessarily 0, and we'll show that this is not 0. Okay, so this will actually be very interesting to do. This will actually depend on just one point of that, wherever it's not. It's like a delta function. It's a very nice identity. As of now, good? Okay, no confusions? Okay. Yeah, I struggled there a little in the notations. Okay. Okay, so with that, so if I can evaluate that, I'm good. Since it is a small circle around it, I will also give a radius to that circle and take the limit of that circle really going to 0. Okay, so we are going to take C prime to be having a limit epsilon radius going to 0. So there will be a radius of this circle, which will be epsilon prime, let's say, because it is C prime. Yes.
Oh, actually, that was my question.
Oh.
Sorry. Yeah.
Okay. Okay. Yeah. Okay. Okay. So we have to just basically evaluate this, and let's do that. So again, with all that struggle with the notation, I have I of A. I have shown that that's equal to integral on a contour that runs counterclockwise, and in the limit, so yeah, I will define that dz of z minus A, where C prime is a circular contour, and this is epsilon prime, and this is C prime, contour is C prime, and the radius of that circular path is epsilon prime. Clear? Okay, so if I can evaluate that, that's good. And whenever we have a circular contour, a good thing to notice is that we can put r sine theta, right, or r e raised to theta. So we want to go along this path, right, on the variable that goes around is angle theta. Right? So I don't have to worry about the radius, that doesn't change in this integral. So I substitute. Z equal to A plus epsilon e raised to it. What am I saying here? A, remember, could be a complex number. A we usually associate with the real number. What is A? A is this. That's your A, is a complex number. A is that point. Okay? And then I'm going around that A, I'm going epsilon e raised to it. Is that clear? It's like saying, this is my origin. If I think of it as vectors, that's my A, right? That's my complex number. And then around that, I'm going in a circle. So if you want, this is my angle theta. So that makes sense. So let's say this is my angle theta. And that's epsilon front. Is that clear? Right. So complex number A, and then I'm going around that A with a radius epsilon and angle theta B. And when I'm doing this integral is on angle theta, not an epsilon. Right? Epsilon is fixed on that circle. So that's my substitution. Since it's a contour integral or it's a path integral, there's only one variable I'm integrating on, that's angle theta. And so I want to capture that. So dz here actually has only one real variable, and that's theta. So that's 0 plus epsilon I brings down when I differentiate, and then there is e raised to I theta, theta. Clear? So that's that integral, and that integral is actually, even though we write dz, it's actually an angle. At least in that contour, that's only an angle, one parameter, right? A path integral can have only one parameter. So that's okay. So now we substitute back. So now I want to write it in simple integral notation instead of the complex integral. That's equal. This integral is nothing but theta going from 0 to 2 pi. Right? Now I don't need any contour to represent that. And dz actually is I times epsilon times e raised to I theta d theta. Correct? F of z now. Z is equal to a plus epsilon e raised to I theta. I'm integrating on theta. It appears here. And z minus a is epsilon e raised to I theta. Is that clear?
Yeah.
Okay. Once the algebra is clear, I want to point out a very important step that happens next. Okay. Is the algebra very clear? Very comfortable with it. Once algebra is taken out of the picture, notice what was happening. Why was this not analytic? It was an infinity, like z minus a was blowing up. Okay. Now, with this way of doing it, what is happening? As you get closer and closer, you can get as close as you want. Doesn't matter. This cancels out. Right. Sin x by x, why is it 1 and not 0 or not undefined? Sin x by x, what is that equal to? Limit x tends to 0. Right? It is not undefined. It is very well defined. That's 1. Why? Because there's a 0 in the denominator. That is exactly the same value in the numerator. It cancels out. You have well defined. Same thing. Once this cancels out, this is well defined. Before that, it's not well defined. Because if you divide by 0, it's not defined. We don't know what that is. We don't know how to do algebra with that. And we don't know what that means. It means that we don't. Algebra is not okay. 3 plus 2, 3 plus infinity, we don't know what that is equal to. Right? So that is not, but the moment this goes away, so if you go around it, you can go as close as you want. But as far as you go around it, is well defined. Right? So you can, even for infinite quantities, if you go around it, it's very well defined. That's the nice feature in here. So this cancels out. In fact, this also cancels out. That's an important step, and that allows us to now do this evaluation. Now that's equal to I comes out, and there's a 0 to 2 pi d theta, and this is f of a plus epsilon e raised to I theta. Okay. Now, this piece here, notice this was a large A, right? This is A, and I'm taking the limit epsilon tends to 0. I can come from any direction I want to. This will always be large compared to this. Right? Exponential is less than 1. Right? So this, no, exponential is not always less than 1, but this is whatever it is not going to be infinity, right? Because this is 0 to 2 pi. As far as this doesn't go to infinity, and this is going to 0, this whole thing is going to go to 0 in the limit epsilon goes to 0. So this is a small number compared to that. So in the limit epsilon tends to 0, remember in this contour C prime, we had this limit epsilon prime going to 0. That was important, right? Like it's not that it's for any contour I'm talking about. I would like to take it to the limit. This argument goes through even without that. But if that limit epsilon goes to 0, then this doesn't contribute. A is there, f of A dominates over A plus. F of A is the same as A plus, a really tiny quant number right next to that. It is pretty much continuous, we are saying. That's the main idea. It is continuous at that point, whether I evaluate it at 0 or 0 plus tiny quantity, it's the same. Christian?
Yeah, so your f of z function, that's still the u plus iv, right?
That's still the u plus iv, and it is analytic.
Okay,
It is analytic. Important is that that doesn't blow up.
I see, yeah.
That doesn't blow up at that point. If it blows up, then that is a separate analysis we have to do. We are saying f of z is analytic, and z minus a is not analytic at a. Okay, so it's just it's called a pole. So this kind of non-analyticity is called a pole. Clear? Once this goes away, this is just f of a, right? So change this. This is just f of a. Again, this is the most important step. Okay, rest everything is I'm just clarifying and filling in the steps. Okay. F of A does not depend on theta. Right? It can come out. So that's I times f of A times 0 to 2 pi theta. That's a simple integral. I can evaluate 2 pi. So it's 2 pi I times f of A. Okay. So again, what have we done here? There's an identity here. If you have an analytic function, go around a contour, you have an analytic function f of z divided by z minus a. And if I were to divide by 2 pi I also, if I were to put the 2 pi on the left, I get f of a. So wherever that pole is, that's all that point contributes. Where else do you get such a feature? Dirac delta function, right? Dirac delta function does exactly that's something wherever it's equal to a, it will evaluate the function at that point. But that's just an it is. We will see this more seriously in a few minutes. Okay. Is that clear? And this f of a is called the residue. So this is called the residue of this integral. And this whole thing is called residue theorem. So next time you see a function and then over some z minus a structure, you don't need to do anything. Evaluate that function at z equal to a and you have the integral immediately. Okay. Yes.
So say that instead of going out to the clockwise, we kept it counterclockwise, it would show up in the
minus.
EI. Yeah, okay.
Minus. It will become the whole thing will minus. Oh, right. There was z here, c, right? Yeah. It will become a minus. That's correct.
Okay.
So the clockwise, counterclockwise made importance here because if I had done the other way, I would have got an exact opposite. So the way in the beginning, the confusion I had was important. So I corrected it and we got the right answer. Okay, so this was C prime. Okay. Any questions here? So this is the basic thing. Now we'll start using this in examples. Okay. So let's evaluate a simple. So we have about 20 minutes and I should leave you guys a little early, right? When you have an exam. So let me directly go into the integral. This has this interpretation with causality. In physics, always we have causality being used. So what is causality? What is causality? In the way In words, let's say.
Cause and effect.
Cause and effect, very good. It means that something in the future cannot affect me. What has not happened cannot affect me today, right? And there is no reason for us to believe that as far as physics goes, but we never see such a thing, that future affecting us. So it's a good assumption to make that physics and nature itself is causal, right? Just based on experience. Tomorrow an example comes where it's not causal, you have to break this, right? It plays an important role in the sense when we are constructing theories. Sometimes you do talk about non-causal situations, but there is a good reason, or based on this, we have never seen it, you would not believe it. But there are situations where we don't have to believe it. For example, in atomic physics, we don't know whether it is there or not. But again, having said that, as of today, the consensus between all scientists, let's say, is that all the theories we have as of today is causal. And any non-causal theory is looked upon, like it is scrutinized a lot. So if you want to construct a non-causal, you should construct, yeah, you should venture out, but it should be scrutinized significantly. So we will stick to causal situations. So how would you put causal situations in our physics? Where else where do you see it? The simplest function that defines that is called a Heaviside step function. It's a simple function, but if the moment you put in time in there, it becomes very special, right? So let's say t is time, and it says that there is a function theta of t, which is equal to, let's say, 1 for t greater than 0, and it's equal to 0 for t less than 0. That would say that that's one of the simplest functions you would think of, right? But the moment I put this in if I have Maxwell's equation, I put in a theta function, then it's causal, right? That's the easiest way of modeling causality, if you want, right? But that is putting it by hand, right? It's not a fundamental, something has not implied this, right? You would like this to happen. So it does come in various, when you're modeling, this is the way you would put in causality. But now it is also true that many things you study in frequency space. What is the thing that you study in frequency space, for example? Give an example of something that you study in frequency space. Frequency means frequency dependence of that property is studied.
Digital electronics.
Digital electronics, yeah, like whatever we hear, that's a good signal processing. But time and frequency are related, is that correct?
Yeah.
And why is that related?
Fourier transform.
Fourier transform. Like music, for example, acoustics, we think of it as a sum of lot of oscillations of a particular single frequency. Lot of oscillations of single frequencies. Okay. So what is a Fourier transform? Let's say f of t. This is some music you can think of as a function of time. Like music is intensity of, let's say, intensity of
the wave.
Intensity of the wave, or intensity of audio waves. Yeah, intensity of pressure. Yeah, so pressure at one point, right? Pressure at one point, let's say right next to our eardrum is what decides what we listen to, or next to the signal. So some pressure wave decides that, but that's what f of t is. If you want to write it in the frequency space, you would say this is a sum of a lot of frequencies. So it's d omega by 2 pi e raised to minus I omega t. This is, if you want sine omega t cosine omega t, it's good to write it in exponential. And this is f tilde of omega. This is the amplitude of each wave. So this is minus infinity to plus infinity. So that's Fourier transform. We are saying that in terms of more accessible physical quantities, intensity of music right next to a detector, how many of each component, so this is a component in the sense here you would say, is it tones or overtones? I think when you say music is in terms of ABC, right? What is it? In Hindi, in India it is Sare Gama, but in
Octet or something.
yeah, octet, what is it?
Like octaves?
Yeah, 8 of them. What do you call them? I thought it was A, B, C.
Right. I think they're like chords, right?
Yeah.
I think it's almost same 8, but the classification of names are
Yeah, what are the
different.
names of that? It's supposed to be simple.
GD.
Yeah, I don't remember that. Okay, doesn't matter. But yeah, but in general, it is a sum of all possible frequencies. Omega is real here. Every possible frequency something can oscillate with, and each one contributes with this amplitude, right? And that's what a Fourier transform is. Now, let's say, what's the Fourier transform of this? Now, what happens is that some physical quantity, let's say refractive index of a material, that's color dependent, right? For red light, it behaves differently, green light, it behaves differently. This could be your frequency dependent refractive index. Okay. But we work in the real time. Okay. How a wave behaves in time inside a material is this. But the property that decides that is a refractive index that's in the complex space. So we would like to know when we say something is causal, what is that in the Fourier space, right? Because the material properties are given in the Fourier space. In the frequency dependent part, refractive index, for example, is given in omega, and omega, this is a complex function, right? Because this is complex, like this is real. This could be complex, right? So the refractive index, when you say there is a real part of the refractive index, there is an imaginary part of the refractive index. But overall, this is a real quantity. And let us say that it respects causality. So something, this has to be called, this 1, 0 has to be coming in. So how do you, so the question that comes in is that this function, how do you see it in the real, in the complex plane, in the frequency space? A simple function like this, which is very intuitive, 0 before, 1 flat, this thing, how does it look like in the frequency space? So you would say that, okay, I will put this inside in here and invert this. There is an inverse Fourier transform. So let's see what that is. Let me put this as theta. So this is theta tilde, that's theta, and theta tilde, frequency space, as an inverse Fourier transform. That's dt e raised to I omega t, and this is of t, and this is again right. And but now you can integrate this because this is just 1 or 0, right? So put in this value in here. It is 0 for t less than 0. So when I do go from minus infinity to 0, it doesn't contribute. So this is basically saying that this is equal to 0 to infinity dt exponential of I omega t. And now I can do that integral because this integral is exponential integral. How much is that? That's equal to exponential of I omega t over, I'm integrating over omega, and then I have to evaluate at t equal to 0 and t equal to infinity. And now tell me, what is this equal to? What is this function when you evaluate it at t equal to infinity?
Infinity.
And why is that? This is exponential of I omega. Omega is real, right? I, so it is cosine omega t plus sine omega t. Cosine and sine functions are between always less than 1 and minus 1, right? So it is surely not infinity, it is between minus 1 and plus 1. But still, what is it equal to? Is that clear what I'm asking? Like this is cosine omega t plus sine I sine omega t. But when t is equal to infinity, very far away, it keeps oscillating, but where? Where does it end exactly? We don't know. So this is not defined. You cannot conclude what this is equal to right by looking at it. Or in fact, it's not well defined. Right? Is that clear? I'm saying? It's not well defined. So a simple function like this causality, when we say, if you want to put this in the frequency space, there is a challenge you face immediately. So what is that equal to? And you face this in quantum mechanics also, right? Wave functions of free particle, or again in Fourier space, there it is the momentum space, right? Position and momentum space. Position in the position you are well defined, but the moment you go to the momentum space, it is spread out completely, right? And then you say that, oh, where does it end? What is the value at somewhere at infinity? It's not well defined. And you face the challenge there also, and then you have to place some. You have to make this more meaningful because we want to work with this, right? So you want to make this more meaningful. So okay, I go back and say that, okay, what can I change? Omega doesn't have much meaning here, right? But I can change t a little bit. So I can say this was t equal to 0, right? At t equal to 0, there is a special property. I say that, how about, let me just change this to omega. Like this inverse integral, I'm going to change this to omega. Check what I want to do. Because I want to, okay, minus delta t. I want to change this by minus delta t. Let me change this by omega plus I delta t. So at this point, I put in a small delta. This is saying that limit delta tends to 0. And we want to see whether this changes anything or not. Okay, this whole integral, I put in a small delta in there. And how does it change? And here right away, you would say that, oh, it seems like it doesn't get affected. So I think I should be able to do it. But that is provided I get a meaningful answer in here. Right? So you're changing something, an additional limit here. It's like saying whenever something goes to infinity, I want to see what happens. I'm going to go close to that, right? At omega equal to, here the limit is on t, right? Not on omega. So maybe I can play with omega and still get away with it, right? So this is a question as to, okay, what do we want to do here? So we are going to put in a small change in omega there and see what happens in there. And let's do that again. So this becomes I square is, oh, I want to make a minus actually. Okay, so minus and a minus plus. So this is e raised to minus delta t. This is minus plus I squared with minus, and that is a delta t. Right?
So it's minus I omega t2.
This is, oh, what did I do? Yeah, this should be minus. Earlier I made a mistake here. Apparently I was copying.
It was not minus.
Oh, no. This is okay. What is happening?
Oh, because it's in frequency space. Right?
Yeah, this is in
I
the.
see.
No. This is wrong. Give me a second. What am I doing? Hold on. This is better. Okay. Let's change this in a more. Okay, so that's our theta space. This is exponential. This is the correct one. Okay, and theta tilde of omega. Okay, so that's no doubt about that. Okay, and theta tilde would be equal to this. And I want to kill this time somehow. Yeah. Let's put it here. So I can always put this in here, right? So this is e raised to minus delta t. Right? Put that delta t in here. So this is exponential of minus delta t. But in the limit, delta tends to 0. Clear what I'm saying? One. This is the same as limit exponential of delta t, and this is 0. This is for t greater than 0, t less than 0. Oops. Confuse again. Because one can be written as a limit. There it seems to be very innocent, but this is going to save us in interpreting here. Right? So when I substitute this in here, I put in a delta t there. Right? So this is theta of t, sorry. And for Rob's case, I should show that and again bring it back. Okay. So now this is equal to exponential of minus delta t, and this is limit. And that should leave you guys in the right time. Delta tends to 0. That's equal to limit delta tends to 0, 0 to infinity dt. I want to write this as exponential of I omega plus I delta times t. Correct? Which is limit delta tends to 0 of exponential of I omega t and exponential of delta t at omega plus I delta and I, right? Is that clear? What I did some, like, this was what I introduced, but then I followed it through and I reached here. And this is where we were stuck earlier. But now notice at t equal to infinity, what is this? Earlier we were having this, but that is between -1 and 0. I just don't know what it is, but it is between -1 and 0. What is this at t equal to infinity? Now exponential function at t equal to infinity, exponentially decaying.
1 by irreducible.
Yeah, what is that equal to? At t equal to infinity. It's 1. T. At t equal to infinity, what does it become? 0. Right? Surely 0. So earlier we were not able, we didn't have this, right? So this was between -1 and 1. So we don't know what it is. But now this gives value to that. That makes it a 0. Is that clear how I made an undefined function? I converted it into a well-defined function. Right? That is the only, so with that delta I have done, right? So that's the trick I did. And so the t equal to infinity I can forget. And at t equal to 0, I don't have to worry. This is 1. So this is equal to my limit delta tends to 0 minus of 1 over omega plus I delta, and there is an I in front. That clear? Okay. This is what this function looks like in the Fourier space. Okay, very hard to interpret that, right? So now if I were to tell you that, okay, I want to check if a material properties are causal or not, like given a refractive index, is it causal or not? It's not easy to check. You have to check that, okay, is it of this form? if it is plus or minus 1 alone, forget the other dependence, it should at least have this structure. So we will investigate this and we will actually check that in the contour integral, how does this work? Like, we'll do the same integral again, but now in the contour, how does it work? But I'll leave you guys before that and we'll do this on Monday. Sorry, I got confused here and there. That like took some time. Kishan?
Yeah, I
Yeah.
just have a question about these contours and stuff.
Mhm.
So like it seems that when like, I don't know, I keep thinking like the clockwise and counterclockwise is related to some curl of this like surface, and I don't know
Yes.
why I keep thinking that.
It is that because analytic function, if you were to think of it as a vector function,
Right.
like xy,
Mhm.
then that means that that function has a well-defined curve
Yeah.
in the vector field sense. So think of 2 dimensions electric field,
Mhm.
right? We usually work in 3 dimensions, that's different. Think of a 2-dimensional electric field, that means everything should have cylindrical symmetry. And then ask what kind of electric field can become a good analytic function, can become a good representation of an analytic function. Those are electric fields that have a curl-free electric fields. Curl should be equal to 0. Now you say electric field is a vector function. This is an analytic function. Analytic function has 2 components, U and V. Right? It's very constrained, and there is a 1-to-1 correspondence in there. And I kind of very hand-wavingly said once that if you have U as your potential, then V is your electric field lines. Not electric field, because electric field needs to be a vector. These are electric field lines. And U and V together does do the job of electric. So you're pretty much defining electric field. So there was a whole work in 1870s or 1880s, I remember, where these are called conjugate functions, but all of your 2-dimensional electrostatics can be done using complex functions. Every problem can be. In fact, you can solve problems that were not solvable earlier using this idea. So you go into the conjugate space, it becomes a simpler problem, work it out, and then you come back. So that's a very powerful technique in there, but it's 2-dimensional. That's a challenge.
Right. I have a question related to this. I mean, I have issues with this one in electrodynamics too. When you are doing line integral or something.
Yes.
So when someone says this charge is distributed on the surface, so it is not actually enclosing the whole bound, only the boundary or the I mean the meat of this, and like if there is like this, the charge is someone says the charge is on the boundary. So there is a charge inside.
There is no charge inside.
Okay, so
Which means inside is 0. It's a very strong statement. Is that clear? So for example, so the question here, I think what you understand is that, let's say this is a conductor, right? And conductor by definition, all the charges will move out, like it's free to move. So all of them will be here.
Here or outside?
It's on a very tiny 10⁻⁹, 1 nanometer difference there. In reality, this has been measured that within all the charges are within 1 nanometer on that conducting boundary. It's not 0. Ideally speaking, mathematically, you would really like it to be on the surface 0, but it's about 1 nanometer. That's a maximum. That's called the skin depth of a conductor. So it's within 1 nanometer. So it's on the surface here within that 1 nanometer. Is that your question?
Yeah. So I'm analyzing this one with that one.
Correct.
So in contour integral, we are actually using a curve.
Curve. This is a surface.
Yeah, surface. But in that scenario, you are taking the whole meat of this. I mean the under scenario too. But you are actually integrating over the curve.
Integrating over. So here, there's 2 differences. That this is the Gauss's theorem. There it is the Stokes theorem. First, let's differentiate that. Right. So don't confuse in there. But this is the volume. Right. In this context, you say the volume integral is the same, is decided by the surface integral of something else. Is that clear? This is a very strong statement that It's almost like saying that what happens to me here is decided by something on the edge of the universe. Doesn't have to be correct, but that's what is true, which is why it is. That's the power of Maxwell's equation. It is really like saying that at the edge of the universe is just, or the sum of all the edge of the universe is deciding my life. I wouldn't believe that, right? But for a conductor, that's pretty much what it is. It is the edge of the universe. I mean, it will take forever for that electron to travel to the edge if it were to go slowly. It's a lot of space in there. But really, that electron at the center, if that is here, that cannot be an electron there, right? That's a conclusion we make. There's no electric field at that point. The electric field is zero. It's a very strong, it's a constraint basically. It's a natural constraint dictated by the nature. Right, so it's a fundamental statement. Did I answer your question?
So, I mean, so how we differentiate between this one and that one, apart from the Stokes theorem you mentioned?
There is no difference. If you put a charge or the connection between the two is that, suppose there, don't go by the conductor, let's say positive charge. Okay, there is an electric field here, right? This one. Now, if I were to calculate 1 over, there's an electric field is 1 over R. Do this exercise. So 1 over R square, right? If I were to do 1 over R square, take the gradient of this, the gradient dotted with E. Right? It will come out to be 0, exactly 0, right? It's 0 everywhere. That's in the volume. It's 0 everywhere. If I add up all the zeros, I should get a 0. But it's not 0. If I do an integral, if I add up all this integral, it's not 0, it is a charge.
This is the Dirac delta function.
It's a Dirac delta function. That's what this is. This is the Dirac delta function analogy. It is 0 everywhere, as close as I want, but that point contributes. You cannot ignore that point. That's the Dirac delta function. That's the residue. Okay? Here it's a residue. That's there the charge. How much ever closer go, I cannot ignore that infinity. It will contribute, and that infinity is decided by the number of dimensions. 1 over R square cancels that, right? The surface area cancels 1 over R square. Electric field for electrostatics is R square. It's not R raised to 2.0001. It is exactly R square because our dimensions is, we are living in a 3-dimensional space. So same thing here, you cannot ignore that. That is the thing. So that's a 1-to-1 correspondence.
So is it like making a pinhole and then placing like the smallest charge in the conductor, like just a pinhole space for it? Would that be a
conductor? Okay, so I started with a conductor, then I switched actually.
Right. And I guess I'm relating it kind of to this contour. Would it equate to that example?
Think of a not pinhole, of a elongated charge, a line charge.
Okay, yeah. Sure.
Yeah, line charge is exactly that.
Okay.
Then the question comes, what is the analytic function associated with the line charge, right? And there is an analytic function. Earlier, I've given this as homework. If you go to the previous years, I think 2 years back, I've given as a homework as an function associated. Yeah, it's good to have this discussion, but you guys have an exam. I should make you guys go. Okay, good thoughts, good comments. Yeah. Thank you. Yeah, okay, enjoy.